Thank you very much for inviting me and Senator Hutchison to participate in this TAMEST conference. In 2006, Dr. DeBakey presented to this conference. It's, on the slide it says 2005, which was a misnomer. And his talk was on mechanical circulatory assistance. A talk just after his was on aortic aneurysms and dissections, using genetics to unravel the pathways to these fatal diseases. What people didn't know at that time was 6 days before this conference, Dr. DeBakey developed a type 2 dissection of the ascending aorta and was placed at bed rest. When it came time to come to the conference, there was no way that we could talk him out of joining the conference. He says, I'm going there. I don't care what the consequences is. It means a lot to me to be there, and I'm going. And he went. And he gave a fantastic lecture. This is a CAT scan showing the aneurysm that he had of his ascending aorta. 1 month after that conference, he had to have an operation to replace the aneurysm of the ascending aorta, which had grown in size and there was impending rupture. What did we replace it with? Dacron graft that was developed by Dr. DeBakey. What kind of surgery did we do? The kind of surgery that was developed by Dr. DeBakey and associates. In 2007, you can see the New York Times had this picture in there. The man on the table devised the surgery. Well, Dr. DeBakey's interest in pumps went back to his medical school days when in 1931-32 he developed this roller pump. And actually he developed it for experiments in the laboratory, but then realized that it could be used for blood transfusions. At that time they were using from one individual to another, donor to recipient, blood transfusions, and with this roller pump he could measure how much blood was given to each patient from the recipient. Supposedly in this slide the donor and recipient were his brother and one of his sisters. In 1953, the roller pump was then incorporated into the cardiopulmonary bypass, which became a standard of the cardiopulmonary bypass. Dr. DeBakey was very instrumental in developing funds for the NIH to have research funds for the development of artificial hearts and assist devices. And that was back in the early 1960s. This is one of the early devices that came out, which is a pulsatile device, which was used for what we call treatment of post-cardiotomy. The patient was unable to be weaned from a heart-lung machine, and putting this device on the outside connected to the atrium and the axillary artery, they were able to support that patient and after 10 days remove the pump, and she then resumed a normal life. He's still in the laboratory. They were working on a total artificial heart. And after we had a little experience with heart transplantation in 1968, he said this, thus, whereas the life of a patient is not necessarily threatened by the failure of a transplanted kidney, it is obviously imperiled by a failure of a transplanted heart. This threat emphasizes the urgent need to develop an artificial heart, even only for temporary maintenance of life. Well, in 1969, unbeknownst to Dr. DeBakey, Dr. Cooley implanted an artificial heart in a patient with heart failure. And then several days later, the heart was removed and replaced with a patient's homograft heart from a donor. And this was the first use of one of these devices as a bridge to transplantation. In 1982, Dr. DeVries implanted this artificial heart in Barney Clark as an experiment in destination therapy. Well, our first encounter with being somewhere close to the space agency was in 1997. We saw this in a TASS publication while we were over in Russia, where we had a joint program between the United States and Russia in developing an artificial heart. And this was celebrating the 60th anniversary of the Russian Revolution, and they were highlighting what they considered some of the highlights of accomplishments during that 50-year period of time. And there's a picture of myself and Dr. Shumakov on the bottom, who were with our artificial hearts, and then there were the astronauts and cosmonauts on the top. Well, what do we use these chronic heart assist devices for? We use them for a bridge to transplantation, bridge to recovery, which is about 10% of the patients, or permanent, which is going to be the most common use of these devices. In the mid-1980s, we had several pulsatile devices that became available to use and this primarily is bridge to transplantation. This is an extracorporeal pneumatic pump, the Thoratec. This is the Novacor, an electromechanical intracorporeal pump taking blood from the left ventricle and going to the ascending aorta. And this is a HeartMate family. The one on the the pneumatic was the first of those, and the other one was a electromechanical. The electromechanical one was the first one that was used for destination therapy in a trial called the rematch trial. And after that trial, they determined that the assist device had better results than just medical treatment alone in these patients. And then there's a total artificial heart that is now the Cardio West. Well, these devices all work, but they're very cumbersome and they're difficult to manage. So what we wanted to do was develop a device that would be easier and more reliable, smaller, and more accessible to the patients. So we went to NASA. And this was back in 1988. And to give you a little history of the device that we were working on, we went there in 1988 rather. Micromed was a company that was then designed to, or developed to continue the development of the pump and marketing the pump, was incorporated in 1996. Our first human implant of the axial pump was in 1998, which was 10 years after we had started working on it. And up to this time with this particular pump, we've done 451 implants. So what did we decide was the way that we were going to go as far as propelling the blood? Well, we decided we'd go with an Archimedes type principle, which was of course not anything new. It started at 300 BC. So what did we use to help us out? We had, of course, the experience of the engineers at NASA who were using this type of a pump for transferring fuel in the shuttle, so they had some idea how it worked. And then we went from using CFD, and this was very instrumental in helping us design the pump and fabricate the pump. And to have our verification of our CFD findings, we used PIV, particle imaging velocimetry, to visualize what was going on with these particles as they went through the design pumps that had been fabricated on the CFD findings. After we had a pump that would pump the required 3 to 5 liters per minute, we had to test it and see how it would do against blood. And so the first test that we did against blood, almost every red blood cell was completely destroyed within a minute. So we had to go back to the drawing board and do some work on it. And it took a long time getting things going. I asked the the engineers, I said, you know, I don't understand why you can put a man on the moon and you're having such a hard time getting a pump that's not going to tear up the blood cells. They looked at me and they said, well, they gave us a hell of a lot more money to put that man on the moon. So it just shows some red cells that were torn up. We had other testing that we had to do, vibroacoustic bearing testing. One of the things that was a concern that these bearings would wear out. Well, we found out that these bearings don't wear out, and pumps that have been in over 7 years have had shown no evidence of bearing wear. So that hasn't really been a problem as anticipated. We had to do reliability testing in mock pulsatile loops. When we had a pump that we were happy with, then we went to the animal. First we did ex vivo, where we put the pump on a saddle on top of the calf, and that way we could look at the pump after a day or a week or 2 or 3 weeks, and we could use that same calf for evaluating multiple pumps. And after we were happy with that, after about 51 iterations, we went on to the in vivo, where you can see the calf on the other side, where these were put in up to 6 months. So this is what the pump looked at when we finished and we were getting ready to go clinical. It was a continuous axial flow pump made out of titanium, flow liters up to 10 liters per minute, and our RPM of 7,500 to 12,500. And then this technology was licensed from NASA. Well, how did it compare with other pumps that we were using? Well, you look at the ones on the top, the Novacor and the HeartMate, and look at ours on the bottom. So we made a significant difference in the size of the pump and made it much easier to implant and it could be placed in a larger variety of patients, providing the same amount of circulatory support. But there is still a lot of concern whether you can use non-pulsatile flow to maintain a patient, and so there's a lot of skepticism. Well, our studies in the clinical arena then later showed that that's not the case, that these can be supported very well with just the continuous flow. These are the way, this is the pump configuration, both a child, which is on the left, on the upper, and then the adult pumps. Well, along the way, this is what we received just actually before we put in our first in man, a Space Age Technology Hall of Fame, and we were inducted into that, and these are the engineers at NASA and Baylor that were all awarded together for this space age technology. So this is the way the pump was implanted in man. You can see there's a pumping going from the apex of the left ventricle to the ascending aorta with a continuous flow pump. There, on the man side, you can see a little white thing on the graft on the outside, which is a flow meter, which gives you real-time flows of the pump. And if we didn't put it through a sternotomy, we could put it through a left chest like you see here. This is just a picture of Dr. DeBakey and Dr. Roland Hetzer in 1998 when we did our first clinical implants in Europe, and I'm down below with Dr. Matthias Lobe, one of his associates, and then later one of mine. This is the first patient that we put the pump in here in the United States in 2000. These are the first application of the pump in children. This is one from Arkansas. And then you can see these patients after the pump has been in place, out away from the hospital doing normal things. Exercising, we found out that they could exercise just as well as those on the pulsatile larger pumps. They could get up to 100 watts without any problem. And so what did we learn from our early clinical experience? Well, one, these patients with a continuous flow, which produces a pulsatility at times, can be resuscitated, they can be rehabilitated, and they can be maintained on this type of pump. And so today, from that experience, almost all of the ventricular assist devices that are being placed are continuous flow, either axial or centrifugal pumps, and you don't see any more pulsatile pumps being developed. One of the problems that we encountered in our clinical experience was a small percentage of patients would develop clot, like you see here, by the bearing. So after this had occurred in about 10 to 15% of our patients, we decided to put a temporary hold on clinical implants and go back and see if we could do something in the lab and in redesigning this to prevent that from occurring. So over a period of time from 1998 to 2010, we made multiple changes, and I'll just go through some of these. Part of this was a cannula change with a connector and making it much smoother so that there was no seam. We used CFD results, and we looked at the hubs, and there was an increased gap that we were able to produce improved circulation pattern in the rear hub, so that made a significant difference. Narrow areas of stasis. Then we looked at the front hub, and then we made more changes. These are all because of CFD evaluation. And then looked at the angle of inlet angle on the impellers, and it showed that we increased that, and we got better to enhance the pressure responsiveness. And CFD confirmed this, or we confirmed it with CFD. Then we went to the bearing, so we were at the front hub, the rear hub, and made some changes in the impeller. And then we made changes in the bearings and went from a shaft and bearing to a ball and cup bearing. And you can see there's a ball and cup bearing. There's very good flow through there with good washing out and no recirculation. This shows after we'd stopped and we had done these reevaluation and made some minor changes, we went to the animals and implanted in animals, and here's the ball bearing or the bearing that was in an animal for 60 days without anticoagulation with no evidence of any clot at all. Then we did studies of the platelets, which showed that the PDF on the upper shows there was a marked shift to the left with lower stress accumulation and reduced thrombogenicity. comparing the old and the optimized version, which we were presently working with called. Now, the next one down below showed that there was an order of magnitude of lower platelet activation rate with the optimized design versus the original design of the pump. So we made significant difference in the effect of the pumping on platelets. So when you look at the Heart Assist 5, which we finished up and now back in the clinical arena, we had optimized the blade tip clearance. We made stronger magnets. We trimmed the inducer blades. We streamlined with three-bladed flow straightener, and we had silicon carbide ball and cup bearings. Looking at the whole device, it looks like this, where you can see the diffuser, the stator, the housing, the flow tube, the inducer, and the flow straightener. So how do we control this pump? Well, there is a controller which is in the small box below the pump, and then there is what we call the heart attendant. The controller is what is used to set the RPMs and the alarms, etc., for the pump. And that's something that the patient carries with him all the time, along with a couple of batteries. And then the attendant, what it does is allows remote monitoring via the internet. It collects and stores pump parameters when connected to the controller, charges and reconditions the batteries, provides wall power to the VAD, and programs the controller and sets RPM and thresholds. And this is sort of what it looks like, where you see the patient connected to the attendant, and then when there's an alarm, it then goes to a central area, then back to the patient's physician, and then to the patient. So what were the clinical benefits of this Micromed DeBakey-Noon pump? Well, as far as the surgeons are concerned, it was easier to implant and explant. You could put it in smaller patients. The patients were less aware, and the drive lines that are going between the controller and the pump were much smaller and had less infection. They were noiseless. Now, the other pumps, the pulsatile pumps that I showed you earlier, all made noise. So you could sit on the ward or sit and close your eyes, and they would march them by, and you could hear the one coming by making clack, 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 another coming by hissing, 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 and you could call them off. You know exactly what they were. But when one of our pumps went over, they never heard a thing because it doesn't make any noise. So drive line infections were down. It provided adequate circulatory support, and it's less expensive. Now, one of the things that we're doing now is expanding to use these pumps as a total artificial heart, where we resect both ventricles and then replace them with these two pumps like you see, with the cuffs that sew onto the atrium and then to the pulmonary artery and the aorta. And today we have a calf that Dr. Bud Frazier has over at the Texas Heart Institute, which is now completing its 51st day on the pump, which was really a world record so far, and it's going on strong. So when you say, what about space-age technology? How was it applied to the VAD? What kind of things did we really use? Well, the impeller design, CFD, PIV, the multi-axis machining, laser welding, ceramic bearings, metallurgy, battery technology. Battery technology is something that we all have as a weakness, because those batteries that we have now, that were first 4 hours, we got some that last 8 hours, but they're big and they're cumbersome, and we need to do better work on getting better batteries. Magnet technology, and then vibroacoustic testing. This is just a picture of on Valentine's Day party in February of 2010. You see all the patients there. Most of them are with family and patients who have assist devices or heart transplants. And one of the differences between this meeting and previous ones that we had is that the previous ones where they had the pulsatile pumps, you could tell who had a pump and who didn't, and there was a lot of racket in the room. And this time, the only racket was people talking, because you couldn't hear the devices, because we had all continuous flow pumps. Well, this is Dr. DeBakey receiving a Congressional Gold Medal. This is pre his trip to Washington, but this was at Baylor College of Medicine. You can see Senator Hutchison there and Dr. DeBakey receiving the Congressional Gold Medal. And this is him in Washington, D.C., receiving the Congressional Gold Medal from President Bush. One of the things that, if any of you were there, that when they rolled Dr. DeBakey up on the podium up there, the person who took him up to turn around and left. And President Bush looked down, and he saw that they didn't put the brake on. So he quietly reached down, put the brake on the wheel, so Dr. DeBakey wouldn't go rolling off. And this is just a picture of myself and Matthias Loewe, the surgeons that took care of Dr. DeBakey and did his operations, and that was 1 month after his presentation here at TAMEST. Thank you very much.